Welcome to Tech Blueprint, a window that lets you know the latest technology news in the world. On March 23, 2025, a piece of news about Samsung's suspension of 1.4 nanometer process research and development caused a stir in the industry. This chip giant, once known as a technological radical, admitted for the first time that the technology leap route was unsustainable after a cumulative investment of more than $80 billion, about 580 billion renminbi. This seemingly sudden strategic contraction is actually a microcosm of the semiconductor industry's transformation from nano-digital competition to commercial value return. Samsung's predicament began with its desperate bet on GAA, all-around gate transistor technology. In 2022, Samsung took the lead in adopting the GAA architecture at the 3-nanometer node, trying to suppress TSMC's FinFET route with a technological generation gap. However, the reality is extremely cruel. Samsung's 3-nanometer yield has long hovered below 20%, while TSMC's process yield has exceeded 70% during the same period. This technological generation gap directly led to major customers such as Qualcomm and Nvidia switching to TSMC, and even Samsung's own Exynos 2500 chip was forced to be postponed due to yield issues. Comparing the technical paths of the two giants, TSMC's incremental innovation strategy is more sophisticated. Although its 3-nanometers process uses the FinFET architecture, it has achieved a transistor density 40% higher than Samsung's 5-nanometers process by optimizing materials and process parameters. This radical in conservatism just meets customers' core needs for a balance between performance and cost. Samsung's technical director once admitted, "We misjudged the difficulty of industrialization of the GAA process, and the complexity of equipment adaptation and process integration far exceeded expectations." Looking back at the rise and fall of Samsung Semiconductor, 2017 was a key watershed. At that time, relying on the 14-nanometers FinFET technology developed by Liang Mingseng's team, Samsung not only mass-produced half a year earlier than TSMC, but also won Apple's A9 processor order from the latter. But with Liang Mingseng's switch to SMIC, Samsung's technology route began to get out of control. The leakage rate of the 10-nanometers process was 20% higher than that of its competitors. The 7-nanometers node missed the window period due to the delayed deployment of EUV lithography machines, and the transistor density of the 5-nanometers process was even lower than TSMC's 7-nanometers level. This technological hollowing out reached its peak at the 3-nanometer node. In order to seize the title of the world's first GAA commercialization, Samsung forced mass production without sufficient equipment verification and process maturity, which eventually led to the investment of $30 billion being almost wasted. In sharp contrast, although TSMC started mass production at the 3-nanometer node a little later, it has taken 97% of the world's 3-nanometer chip orders, with a yield rate of over 80%. Samsung Electronics' internal report shows that its semiconductor division's operating profit margin has plummeted from 53% in 2017 to 19% in 2023. Faced with the collapse of the technology leap route, Samsung's adjustment strategy highlights the change in the survival rules of the semiconductor industry. Technical pragmatism rises. Suspend 1.4 nanometer research and development. Concentrate resources to increase the 3-nanometer yield from 20% to 60%. Accelerate the mass production of the 2-nanometer process. And optimize power consumption performance through the backside power supply network, BSPDN, technology. Deep bundling of the industrial chain. jointly developing domestic EUV photoresist with Japan's Shin-Etsu Chemical and the United States Applied Materials, and exploring the construction of a semiconductor ecological park with China, trying to exchange market for technology. Customer demand front-end. Set up a special management diagnosis office to restructure the performance of the Exynos processor team and incorporate customer feedback into the R&D closed loop. This shift coincides with TSMC's customer dance model. The latter achieved deep synergy between process and architecture through early involvement in Apple and NVIDIA's chip design, and controlled the 3-nanometer cost within the customer's affordable range. Samsung executives said frankly, "We finally realized that process numbers are not moats, but technologies that customers are willing to pay for." Samsung's setbacks reflect the deep changes in the semiconductor industry. Approaching the limit of technology, when the size of transistors approaches the atomic level, the marginal benefits of simply pursuing process miniaturization are sharply reduced. The industry has begun to turn to system-level innovations such as chiplets and advanced packaging, and TSMC's 3D fabric technology has achieved a 40% increase in energy efficiency. Reconstruction of business value. According to Boston Consulting Group, the R&D cost of processes below 2 nanometers has increased by 300% compared with 3 nanometers, but the performance improvement is less than 15%. This makes car companies and industrial equipment manufacturers more inclined to adopt customized solutions for mature processes. Geopolitical variables. The U.S. CHIPS Act requires subsidized companies not to expand production in China within 10 years, forcing Samsung to adjust its global production capacity layout. Its 58% production capacity in Southeast Asia is facing the pressure of an average annual increase of 12% in labor costs. In this change, pursuers such as SMIC have shown their latecomer advantages. It focuses on special processes such as 28 nanometers, enters BYD's supply chain through automotive-grade chip certification, and its mature process revenue in 2024 will increase by 67% year-on-year. This confirms the industry's new survival philosophy: being irreplaceable in a specific field is far more commercially valuable than pursuing technological commanding heights. Samsung's strategic contraction marks a new stage in the semiconductor industry's transition from a technological arms race to a return to the essence of business. As the halo of Moore's law gradually fades, the life and death of enterprises are no longer determined by the nanometer numbers in the laboratory, but by the yield curve in the factory, the cost formula in the customer's account book, and the collaborative efficiency of the industrial chain ecosystem. This lesson worth hundreds of billions of dollars warns the industry. On the scale of technological idealism and commercial realism, only players who find a dynamic balance point can get through the fog of industrial cycles.